Got about everybody here this morning. I'm going to start with a safety video for today. And I'm going to shoot on over to a sec here. Share screen. Share. This guy that does Lyman Universe videos, he's actually got some pretty good stuff out there. And what we're going to do is we're going to look at some tool safety this morning. So let me get down to where I can hit the play button. Got any questions, just stop me and I'll pause it. You guys see it okay?
Yep.
What's up, everybody? Welcome back to Lyman Universe. I'm Jeremy Johnson. Today, fellas, we're going to be talking about tools. I'm a little bit under the weather. Now, if this looks like a familiar episode you've already seen before, it's because you have. I deleted this episode. Brian Earnshaw says, "Did you delete a video?" Question mark. I remember watching a video of you explaining what tools to have as a grunt at Lyman Universe. Sorry, buddy, I accidentally deleted Building Better Grunts, so I'm going to reshoot that episode soon. So, I'm a man of my word, and here we go. Okay, well, the reason I deleted it, my wife was like, "Did you like your own video?" And I was like, "Yeah, I like my own videos." She's like, "Only weirdos like their own videos." I was like, "Man, she's probably right." So I just tried to unlike it, and I totally erased it. So that's why, Brian. Fellas, I'm going to try and make this as short as possible. First off, we're going to hit on hammers. 3-pound sledgehammer. Try and get one with the waffles in the face. If you can't, get you a cutting wheel on your grinder and waffle it yourself. That's not a necessity when you first start, because if you're just like me, every time I started a job, I was, just about broke. So you can bum some of these tools from your dad, your brother, whoever. Here's a good 22, 24-ounce framing hammer. Fellas,
start with, guys, we're not going to use framing hammers. I know we got some that we use on the field out there because, it's kind of in short supply right now. But, when you get on the job, you're really not going to use any kind of framing hammer. And I'll just tell you from the Duke Energy side of it, and Professor Shoemaker can jump in anytime about it as well. Lyman hammers, they come both ways, both slick on both sides of the head, or you can get one slick on one side or waffled on the other side. Duke says when you get tools that you should not modify these tools in any kind of ways. And before they did the waffle face on it, we always had hammers that had slick sides on them. And it wasn't, my first Lyman hammer was not a double-sided. It was like a ball peen hammer on one side and a flat face on the other. So we'd always put it in the vise, take a hacksaw and cut the waffles into it. And then, of course, that's been 34 years ago. So since then, they frown on you modifying or changing your tools. They don't want any. There's a chance if you cut it too deep and you're hammering something, a piece might flake off of that hammer and go in your eye or something. So just kind of be careful how you modify. Just make sure you don't really distort that tool to where it's going to come apart on you at any time.
Why do we use a waffle-sided hammer?
So it don't slip off?
Yeah, so it doesn't deflect off whatever. And you're going to get in some cases where you're going to be stapling and hammering some small stuff. It just gets traction on it.
Yeah.
same thing. Try and get one that has the waffles. If not, you can waffle it yourself with a grinder. So when choking that hammer up on a job, go out there and make it count. Next thing is a 12-inch crescent. Now, you want a 10 and a 12, but for right now, a 12 will get you by. Guys, there's, we all know the wheel will adjust it, but it has a fixed jaw and one that travels. The traveling jaw does not follow. The fixed jaw follows. That is the right way to loosen and tighten. If you go this way,
guys, there is a correct way to use these tools, just like you're going to see with the channel locks. That's the next tool he's going to look at. But you can see that crescent wrench is orange on one side and you know, the natural color of the metal on the other side. And that's okay. That's what we did, that to mark our tools. We'd either have some red paint, white paint, blue paint, or something. I didn't go to the extreme and paint the whole tool. I just kind of like put some paint on the bottom part of the handle, but it's not, you know, you don't want to put paint on anything that's going to be used on energized equipment to track over. So that's just a way of letting everybody know, hey, that's my tools.
While you're sitting right there, he just explained the grip side of the non-grip side. Could you Or you want to see the channel lock part of it first?
Yeah, let me shoot ahead, then I'll pause it.
Roger.
It's a better chance you're gonna bust your little knuckles, so. Good crescent wrench. Same thing, 420 channel locks, fixed jaw, traveling jaw, 10, 12 inch.
Back up here. All right, guys, you can see there is a correct way and an incorrect way to use your channel locks. Which one did he say that was? The fixed jaw was on the
Top.
the traveling jaws on the bottom, and that's what you want to do. The direction you want to turn that nut, if you're tightening it, if he's tightening it just like he's holding it right there, if I was holding those pair of channel locks, that's how I'd be tightening one of those nuts on the pole that we're working on now.
Yeah. And you'll notice when you get the channel locks, we used to in our old days call that a speed wrench.
Yeah.
And the teeth are angled not out in this direction on it, they're angled this way. So you can actually use this to get good at it. You can use it as a ratchet, just back and forth, because the teeth grab in one direction and slip in the other. So you've seen thus far, as far as wrenches are, you've seen that crescent wrench and you've seen channel locks. Does he have a alignment wrench? We'll probably see here in a moment.
No.
When you guys are out there in the field and when you're doing construction work on the job, all these are good tools to use. It doesn't mean if you come up to a nut or a bolt that you have to use a alignment wrench. You can use the crescent wrench and you can use the channel locks. They both serve the same purpose as a alignment wrench.
Hey, it's always good to have a good set of 420s in your bag, just in case you have to hold the back side of a nut or something. The whole thing's going to spin. So.
Oh yeah, and when I got hired, you get one set of tools, and the first set of tools I got was a lineman knife, a pair of climb pliers, and a pair of channel locks. That's the only thing they issued you. Lineman wrenches have not been around for a long time.
Yeah, we had to buy our first set of tools. The company didn't, buy us tools. And that's what they gave us a list. They go get you a pair of channel locks, pair of cutting pliers, screwdrivers, all that kind of stuff. But the funny thing is when we went to our lineman school up in North Carolina, outside of Raleigh, the North Carolina people that came into the school, new hires, didn't have channel locks. They just, for some reason, they only used a crescent wrench. We used the channel locks like crazy down here, and they frowned on it a little bit, but they didn't tell us we couldn't use them.
Are the blue handles that are on there, are they insulated? Anybody?
Yes. I'm sorry, go ahead.
The blue handles, are they insulated, anybody?
Yes.
It depends if they're all ripped up.
No, well, even if they aren't ripped up and brand new, those handles are not meant to be for insulation.
Right.
Period.
That gives you kind of a false sense of security when you see those blue handles on there. All right, guys, let's move on to the couple more.
Jaw, traveling jaw, 10, 12 inch flathead screwdriver, great for tightening flathead screws, but mainly you're gonna be prying copper. This is a multi-tool. Don't get one too long because it could be dangerous. Up in the primaries, it could be deadly. These, probably the most important thing you're gonna have on the job. Lineman pliers, fines. Put these in your pocket. So where if you go in somebody's yard or something, dog tries to get you, bam. Or you
Yeah, that works real well. I mean, you always want to keep your pliers in your back pocket, your channel locks. That's kind of a set, channel locks and pliers. The pliers we used to use, I'll never forget, because it was always, pushed into my head, the D2009 NEs. I mean, excellent set of cutting pliers. I wouldn't go anywhere without them. Anytime my truck left the yard or something, I wanted to make sure I had a good set of cutting pliers on my truck.
Yeah, and I have to admit, I don't know what it is about the climb pliers. I've never found a plier that's any better than the Kleins as far as cutting.
Yeah, and you don't want to cut any steel with that. You want to cut aluminum. There is some conductors out there that has a number 2 and a 1/0 conductor to have like a steel core in it. And you really don't want to cut that steel with them Kleins. You can, but it could damage the jaws inside and, kind of tear that up to where they'll degrade faster.
Yeah, and don't hit dogs with them, please. Don't set yourself up for a lawsuit.
Yeah.
anything like that, you're gonna look like a star when you got this, and you keep these in your back pocket. Always have these on you, okay? Because you can tighten something, loosen something, or cut something, or knock something smooth out. Next, a Hawkbill knife. This is a Klein. It's a pretty good brand. If you don't have one of these, this is just the bare bones that first week that you're gonna need. Get your pocket knife. This is a case. It's even got a little lining on there. That's pretty sweet. Try and stay away from ones that has a sharp point. If you can, get the one that has the blunt tip, because when you're skinning, you don't want that thing, you know. Heard some really bad stories.
What he's talking about, that blunt tip, that's the way Duke is going now. I've got a couple Hawk Bills that were given to me from the company guys, and they don't have a sharp point on them. They've got a blunt tip on them. They're so just, I guess, scared that you're going to cut yourself. Of course, there have been some fairly bad accidents, guys cutting toward themselves with a Hawk Bill with a sharp point, and it go through their rubber gloves, go down, cut their arms, and it get stitches. Pretty bad accident from those kind of knives.
Yeah, we got to the point where back in the old days, everybody just brought their own knife, whatever knife you had. And we had some accidents with knives, so they assigned us the telephone, you know, the communications knife and the Hawkbill knife are the ones that you could charge out just to give you the strictness of it. If you used a knife that wasn't issued from the warehouse and you cut yourself, it was immediately an injury on your fault just because you didn't use the right type of knife.
Exactly.
If you have to, you can use your pocket knife, but this is
No,
how I
you
did.
can't.
This is dry and made me plumb bob. Okay, plumb bob. What it's for is plumbing poles. What you do is you hold it like that, and the pole is going to be like here. So you want to bring that pole to where it's straight. Okay, you're going to check it off the front of the boom and at a 90-degree angle off the boom. All right,
Hold
guys,
up.
we got our
Yep.
tools. We know how to use.
So when you're plumb bobbing a pole, guys, I mean, there's a lot of people out there. Sometimes what you're going to want to do, and whatever the supervisor tells you or the crew tells you, they're going to say, well, I want that pole straight up and down. Poles are not exactly straight, are they?
No.
No.
Nope.
You want, with the plumb bob, you're going to look at the top through the string, and you're going to look at the bottom through the string, and you're going to put top over bottom with the plumb bob. Now, some of these, there's deviations that they can have. Sometimes that pole is going to be outside of the string when it comes down the middle, or, you know, up and down the pole. But you need to make the bottom and the top of the pole, and it's what they call top over bottom. Now, sometimes you're going to have to put poles up there where you're going to put a down guy on. Say it's the end pole, like we've been doing the double cross arms, and they're going to do something that what they call raking. That means you're going to lean it the other direction towards the line that's coming off of it, and then tighten up the guy to make it straight. That's so you won't have a loose guy. So that's called pole raking. But as far as the plumb bob is concerned, make sure it's top over bottom. Go ahead.
Angle off the boom. All right, guys, we got our tools. We know how to use them. We need to mark them so we can keep them. The way I do mine is I'll take and put like 2, and then flip it, one, whatever mark you come up with, mark all your tools the same. That way, when somebody comes up and says, hey, man, you got my channel locks. You're like, no, these are mine. He's like, well, how do you know? You're like, well, do you just have 2 and 1 on them? And he's like, what's 2 and 1? And you're like, 2 on this side, 1 on that side. He's like, oh. So you're like, case closed, you win. You can paint them too, guys, but I mean, anybody can get paint. This one here, I was an orange guy on the job. And if you remember from the episode before, I was a red dude. That's good for seeing them from the air. But I mean, you know, anybody can paint the tools. Do not paint the handles, because when you do, they're going to get sticky. They never dry, and it's just a bad idea. Stop from the head up. All right, guys, we got them. We know how to use them. We know how to keep them. Now we need somewhere to put them. So let's go ahead and throw all of our tools. Actually, I want to put that knife where I don't cut myself like last time. Tool bag. Now, when the foreman says, hey, you're going to go grunt for so-and-so, you just grab your little tool bag, and away you go. All right, guys, first week on the job, don't show up when the bell rings. Get there a little bit early, do your walk around. Check your oil, your diesel, your antifreeze, Walk around that truck, check it for flat tires, anything out of the ordinary, something hanging off the truck, all that kind of stuff. Get up there, clean that bucket out. Get you a box, take all that trash out the bottom of the bucket. Don't get under the pole when they're working. It's just not a good idea. You're going to get hit in the head. Guys, walk fast and look worried, okay? That's going to take you a long ways until you learn what to do. Don't be standing there with your hands in your pockets. Every time you catch yourself with your hands in your pockets, I don't know, pinch yourself, do whatever you got to do, but do not be standing around. There's always work to do, especially when you're a grunt. You're in a helper's role. That's not a bad thing. You're just going to be running and grunting for everybody. But one day you're going to be a journeyman. Until then, you know, everybody's been there. So if you'll do this now, it's going to make you better at your job later on. Hey, guys, if you have any action shots, any cool memes, any funny videos, send them to linemanuniverse@gmail.com. Put them on the show. You're going to get a really cool T-shirt. All right, fellas, this week.
All right, guys, a lot of good advice right there about, you know, being the low man, being the new man on the crew, staying busy, stay out of the drop zone. We talked about that a bunch before. Those things are all good to know as well. Just keep yourself busy. Don't be standing around. If you don't know what to do, ask. Those kinds of things. So, Professor Shoemaker, you got anything you want to add to that?
Other than the, you know, as far as we were concerned, and I was a grunt and everything, if you didn't have your hand tools with you, you were pretty much, and I mean with you,
Yeah.
You were scolded pretty hard. And, you know, there's a couple of methods here that, I mean, the minimums, channel locks and those climb pliers and a knife. Those are probably the three minimums you need to be carrying around you on your person all the time. Some guys, I just put my channel locks and pliers in my back pocket, and I had a little pouch for my skinning knife. You'll see some guys out there that are taking a climbing belt tool pouch and cut some slits in it and put it on their regular belt, and they just wear that on their belt every day. But I can guarantee you, and you know, this will make your life a lot easier. You're not going to be working right beside your truck.
Yep.
Backyards, you're gonna have to walk down lines, you're gonna have to walk from truck to truck, and you don't have your tools. Well, they're going to tell you, walk back, get your tools. It's going to save you a lot of time and effort in that situation.
Yep.
Oh, and don't lose them.
Yeah.
You know, all trucks have a bin that you can lock. If you want to keep them in the truck, you'll have a key to that truck where you can lock one bin on it and keep all your tools in. And I hate to say this, I hardly ever shared my tools, but I had them a long time too.
Yep, that's right.
That's all I've got.
That's it. I'm gonna stop share.
Okay. All right, so we're up to me now. Let's see. Let me double check here. Look at some stuff. Mr. Barber. Trevon. Okay, so Trevon left us.
No, I'm right here.
Okay, well, answer. You've done a safety meeting, right?
Yes, sir.
All right, Jonathan Bell, you've done a safety meeting, right?
Yes, sir.
All right, Robert Bamba. Bamba.
Not yet.
Okay, you will be Thursday. Nope. Monday, Tuesday, Wednesday morning. Okay.
All right.
Wednesday morning. All right, gentlemen. So ELW 110 is over, and we are going to be moving to the Electrical Studies for Trades book, ELW 111. And we're going to get more and more involved in electricity, transformation, and all that good stuff. So I also have a video to start us off this morning. So let me get to that. Well, what did I share?
Direct current.
Do you see it in the browser?
Yes. Yeah.
Okay. So we're going to be talking a lot about AC and DC electricity. Now, as far as utility work, electric utilities, what's the most dominant here, AC or DC? Does anybody know? Okay, we'll learn that.
DC.
AC, yes, AC is the predominant voltage type or current type that we're going to be using in the electrical industry. So let's watch this video.
Welcome to our second video on electricity. This one's going to be on alternating and direct currents. So our goals from this video are, one, be able to explain the difference between alternating and direct currents, and later on we're actually going to analyze the pros and cons of each. The first current we're going to talk about is direct current. Direct current is what we call unidirectional. And what that means is it only goes one way. It's like a one-way road or a one-way street. This is just like batteries and circuits or anything with your remote controls and your Xbox, PlayStation, anything like that. So if we take a look down here at the bottom, we have our battery in our circuit. The battery emits electrons, they flow through, they keep going, and they go through this one way. They just keep cycling through this one path. That's all they do. One way, unidirectional. This was made famous by Thomas Edison. Thomas Edison is the one that really tried to use this with their houses and almost powering towns with it. He almost did it exclusively with direct current. But what happened is this man came along and his...
Okay, so let's talk about DC electricity for a moment. In DC electricity, what is the current flow? One way or two ways?
One way.
One way, okay. Simple thing, if you want to apply this to what's in real life out there, what's in your car, AC or DC electricity?
AC.
AC
I
or
mean, DC.
DC electricity? DC, right?
DC's in your car.
Flows out from the car battery, goes to wherever it needs to go, say your headlights, and then flows to the chassis of the vehicle. So that's your ground. Now, what direction does DC electricity flow? Negative to positive or positive to negative? What direction of that one direction? Which way? Negative to positive or positive to negative?
Look like negative to positive.
It is. It flows from the negative terminal to the positive terminal. That is the one direction it does flow. You'll notice also, is this direct voltage or direct current?
Direct current.
Current, okay, keep your mind on that. Same thing is going to happen when we get to AC, alternating current. All right, voltage must be present, but the flow, and like you see the arrows right here, is in a direction. That's why they call it current. Something is flowing.
His name was Nikola Tesla. And he came up with this thing called alternating current. Nikola Tesla actually now has a car named after him, the Tesla. So, alternating current's a little bit different. As its name states, it alternates back and forth. It's bidirectional, two directions. Goes back and forth, alternates back and forth, left, right, left, right. This is what we use in our houses today. And we use what's called 60 hertz, which means that it alternates, it flips 60 times per second, not per minute, per second. So the electricity switches 60 times per second. And we can see that with our little lab activities here. So we're going to first go to direct current, one path. If you take a look at the electrons here, this is using our little PHET activity, P-H-E-T. You can see the electrons are going one way, just one direction. That's it. There's no fancy alternating back and forth. There's one direction. There's flow. Here's a little, let's call it an energizer. Alternating current, on the other hand, switches back and forth. And we can see that over here. You can see the electrons don't really move very far, but they're alternating back and forth, back and forth. Remember, this is a scaled version. These electrons would actually be going so much faster. The one thing you probably see that's different is these light bulbs. These light bulbs are flashing. They're not steadily on like our direct current. What the difference is that when these switch directions, for a fraction of a second, they're actually stopped. They're dead stopped. But inside, the light bulb stays glowing for that fraction of a second. The light stays there. You can't see the difference in between on and off that quickly. So remember, we talked about alternating current is 60 hertz. It changes 60 times per second. This, our little AC battery here, is only going about one time.
Okay, so I'm just going to give you a little information here about what he said. Is there such a thing as an AC battery? What does a battery put out? What does the battery in your car put out as far as current? Direct current or alternating current?
Direct.
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 So there's no such thing as a battery that performs the function of creating alternating current. It's got to be a generator of some type. All right, so that was just a missaying in words. It's got to alternate back and forth.
Time every second. It's changing 1 time every second. We can bump it up to 2 times a second. That's the most that the program can hold. So we can see that they're flashing a lot quicker now. Now imagine this times 30. You wouldn't be able to tell the difference between flashing or on and off. It would just be constant on. And that's what happens in your houses. You can't tell the difference between on and off. You can't tell the difference, but you can't tell when the electrons are switching back and forth. So we're going to jump to another program in a second, but I'm going to show you how this is done. And we can remember that like forces repel each other, electrons repel electrons, and opposite forces attract each other. So we've been talking about magnets a little bit, and alternating current is made with very big magnets moving very quickly.
Okay, I don't want to get any further than that because that's further on than we need to know. The biggest thing that we want to get in our heads right now, the direction of flow for AC. Which way? How many ways?
Back and forth.
DC.
2 ways.
DC.
AC is 2 ways.
AC is bi-directional. It goes one way and then it goes back. Goes one way and back and forth. DC,
1 way.
one way.
One way.
Only. Okay. He talked about frequency here, and I'm going to bring up another screen here, and I'll show you how frequency works as far as that's concerned. But we need to know the difference between DC and AC. All right. DC brought up by Edison in his day, and I think just Edison got more advertisement. That's why he's more popular than Nikola Tesla is. DC is effective, but is not as efficient as AC electricity. Okay, and 2 is creating DC is a little bit more difficult than AC in its functions. AC just has much more efficiency as far as current flow when you're using it. Okay, what time is it? Hey, it's 9:30. Yeah, we'll take a little break here. We're going to start here in the morning. Let's be back here in 15.
Cool.
9:30. Let's be back at 9:45. Okay, guys, it's 9:45, so we'll go ahead and get started back. I will let you know, I'm not going to get into atomic structure too much in the book here. I have moved up to page 12. I'm going to read you a little excerpt here from page 12 in the book. Down at the bottom, electron flow. Electric current is the flow of electrons. There are several theories concerning how electrons are made to flow through a conductor. Do you understand this? And you'll see this in a couple instances through the course here. Is there any proven fact out there in the world as far as the flow of electricity and how it flows, as far as electrons and at the atomic level? Are we able to see it flow?
No.
Yes.
No, we can't see it flow. We can measure the flow of current, but if we were
Oh, I thought you meant if you were looking at a meter.
well, and there are certain meters out there that can show the direction of flow, but can you actually see it flowing through the conductor?
No.
At the atomic level? No. So that's why they have theories out here, and they're going to say theory in a couple times here in the book. And generally, I like to stick close to this theory. I think it's myself, and opinion-wise, and I guess Professor Vermelin would also, that this is the most widely one used out there in the world. One theory is generally referred to as the bump theory. It states that current flow is produced when an electron from one atom knocks electrons from another atom out of orbit. Figure 1-17 demonstrates this action. When an atom contains only one balanced electron, that's a free electron, it is easily given up when struck by another electron. So that's what they're talking about at the atomic level of how electrons are moved and how they flow. So we talked a little bit this morning about AC and DC, and the flow of electrons in DC is one direction. Then when we talked about AC, the flow of electrons are in two directions, bi-directional. So I got a video here I'm going to show you. It's old, but the explanation is very good. Are y'all seeing a share screen?
Got it.
Got it. Here we go.
We've now seen and heard a lot about the flow of current in a circuit. But in everything we've seen, the current has always been flowing around in one direction. Such a current is called direct current, DC. In real life, the direct current causes a steady reading to one side of zero on the measuring instrument.
Now you notice right here, this is what they call a galvanometer. You'll never use one. I've never used one in the utility industry, but it's similar to voltmeter and ammeter, as it measures and it shows the direction of flow. Now, if he swapped the red wire and the black wire, which way would the needle go, left or right?
Left.
Left, right? He's just swapping the direction of flow if he moves the direction of the two leads that are in there. So it's showing the flow direction from left to right on this galvanometer. And this is DC electricity. Notice it's static, it stays in one spot.
But current also exists in a different form in which the direction of the current goes first one way and then the other, and of course is called alternating current, AC. Here an alternating current is causing the pointer in the instrument to swing first to one side and then to the other side. But this is a very slow alteration, and the sort of...
Okay, so you'll notice in the, and we'll get to sine waves here later on, you'll notice when the meter lead or that needle is moving back and forth, it's peaking at 10 on one side, and then it's peaking at 10 on the other side. Is it crossing zero? Want to see that again?
Yes.
Watch what the needle does.
other side. But this...
Okay, and that's relatively slow. They're doing this for demonstration purposes. So through the course of this cycle, it's cycling back and forth. It goes from the peak voltage left to the peak voltage right, and then it is also crossing zero. So at the point in time that the sine wave or the electricity is flowing in alternating current, the voltage is changing in that process.
This is a very slow alteration.
And current flow.
And the sort of AC we will be dealing with changes direction many times in a second. Power generation and transmission for our homes is AC, and there are excellent reasons for preferring AC to DC. Cities, towns, and villages all over the country need enormous amounts of electrical power. To make this power available cheaply, it is distributed at very high voltages, which are far higher than we can safely make use of in our homes. In other words, before we can safely use the power, we have to reduce the voltage somehow. Now it so happens that electrical devices known as transformers can easily change the voltages of AC, either up or down.
So here we're going to get into the meat of it, and it's coming up in the explanation here. Can I transform? And we all should know now why we need the process of transformation. Let me see if somebody can give an example out there. Why do we need transformation as far as our electrical network, our electrical system is concerned? Give me some reasons.
Because you can't use 7,200 volts safely, like for the microwave or fridge.
Right. We don't want 7,200 volts into our home, so we have to reduce it in that manner. What about like transmission voltages? Why do we need, and we spoke about before, we've got Winyah Generating Station down there south of Georgetown. Why do we have to produce at a high voltage down there to get it up to us here in Myrtle Beach?
So you can evenly distribute like to each house.
Right.
Such a long distance.
Long distance, so we can transmit at long distances. What about the economic and construction side? Remember current flow? The bigger my pipe, the more amperage I can get through it. So what happens when I raise voltage? What happens to my amperage?
Amps go down.
So I can use a smaller pipe, right? So I can use a smaller conductor all the way from Georgetown to get it up to here. And like the previous person has said before, now I can transform it again and feed a lot more customers off a smaller conductor that originated south of Georgetown. So it's the economic side of it too. All right. And I'll throw this question out before we get in more depth in the video. We obviously know now, can we transform AC to AC? Can I take an AC voltage at 7,200 volts and convert that 7,200 volts to a 240 volt AC voltage?
Yeah.
Simple
Yes.
question. Simple question. We've done it many times in the process. Yes. Can I convert an AC voltage to a DC voltage? Now, be careful here. What's in your
Yes.
phone? What powers your phone?
DC.
DC, correct?
Battery.
The battery, so that's DC. So can I convert AC to DC to charge my phone?
Yes.
Yes, you can. Okay, so that is a process. Can I convert DC to DC in transformation?
No.
No, you cannot. So this is why AC, when I say the existence of AC, this is why AC is so practical to the utility industry. And it all has to do with transformation. I can raise my voltage, I can lower my voltage for all those economic purposes and needs that I have. You know, I definitely don't want to put 7,200 volts into my house. I want to put 240, so that can be transformed. DC to DC cannot. Now, you spoke earlier when you saw Thomas Edison. Think of it. I'd have to have generating stations and batteries placed everywhere for DC to be able to feed a city. So that's just not practical. And then my conductor size would have to be huge. AC, because of the process of transformation, is the most practical and economic to use.
Transformers cannot change DC voltages. There are literally hundreds of bits of electrical equipment requiring a lot of different voltages. And again, if we use AC, we can make use of transformers to produce exactly the right voltage for each piece of equipment. Alternating current, like direct current, is measured in amps, but with a difference. Let's see what the difference is. Take 1 amp DC. When 1 amp flows, a known very large number of electrons passes a point in 1 second. Well, it's the same for AC, except that the electrons flow past the point in one direction, then reverse and flow past in the other direction. Suppose we have a simple circuit in which, using some sort of switch, we can make the current flow either way through the resistor, and we plot on a graph the current flowing at any moment. For a little while, with the switch open, there is no current flowing. Then we switch the current on in the positive direction, and at once we have a positive current flowing in the circuit. We show it above the zero line.
And you'll notice here, it goes up in this current line, on the white line right there. All right, is it alternating? Is it going up and down?
No.
No. So what kind of current is this, direct or alternating?
Direct.
Correct, absolutely. It's up to the positive side, is flowing in that direction from negative to positive, all right, and it is constant unidirectional.
Then we quickly reverse the direction of the current so that we now have a similar negative current flowing, and we show that below the line. Every time the current reverses, the graph moves to the other side of the line. This is a waveform of a simple alternating current.
Okay, I don't like the graphic that they're showing right here because they're doing it through switching processes. We're going to do it through generation processes here in just a moment.
Now, in most circuits, in practice, it isn't a sudden, instantaneous switch of direction like this. Usually the current builds up one way and then decays down through zero to build up again in the opposite direction, before decaying back again to zero.
All right, so the top one was a switched DC current. It was direct. What is the bottom one?
AC.
AC, exactly. Now this is an alternating current through the bottom. And once again, I will explain. The top line at the peak, is there voltage present there, current at its peak? Yes or no? Got my mouse right over it.
Yes.
Yes.
Yes. How about the bottom?
Yes.
Yes. Okay. There's voltage present and and current at its peak right here. Right. That's not to say that all through the wave voltage is present. So I'll give you an example. If the peak is 120 V here and the valley is 120 V here, halfway through the wave on both sides is 60. 1/4 part through the wave is 30. Now this center line right here, what is the voltage current flow at the center line?
Zero.
Zero. Thank you. Zero. Thank you very much. As in the previous video that you saw, if you think about it, if you look up at an incandescent light bulb, all right, do you actually see with the naked eye 60 times per second no voltage going to the light bulb? It's turned on. Can the naked eye see that?
No.
No, it cannot. Okay, but it does happen. It is happening right here. 60 times per second. You're going to be seeing this zero process happening right here. And actually in one full wave, it's what? Times 2, 120 times per second. This is 1 right here. You're not going to be able to see voltage, but the naked eye cannot see that. 2 is voltage is present through the entire wave, peaking here at the top, but still present until it reaches 0, building, peak, dropping, 0. That's alternating current.
Gradual build up one way, decay. Build up the other way, decay again, and so on. This produces the sine wave.
Okay, so what do we call this?
Sine wave.
Sine wave. Remember that. That is one sine wave. All right, one sine wave. How many times per second does one sine wave happen in electricity, AC electricity?
60.
60 times per second, one wave happens. The simple definition here, guys, is 60 hertz, HZ, not HTZ, like you saw the other guy put up. So what type of electricity do we use in our homes as far as frequency is concerned?
Alternating.
Alternating current. I'm asking the question of frequency. What frequency is it at?
It's 45.
60 hertz. Okay, remember that part, 60 hertz. That's going to be a future quiz question right here. 60 hertz is the frequency at which AC electricity is produced. Now, we've talked about this a little while before. Does that mean it's at 60 hertz when it comes out of the generating station? Yes or no?
No. No.
Why would you change it?
So you can get it to the customer without it changing both ways.
Okay, remember, whatever I do to my electrical properties, anywhere in any process through the entire system, it affects the whole system. So I'm going to produce electricity at 60 hertz, and I'm going to consume at 60 hertz. All right, there's no need. Transformation does not, I'll say this again, does not alter the waveform of AC electricity. I want it 60 hertz throughout. I don't know if you ever looked at the charger for your phone. I know they're hard to read, or something that you plug in to charge golf carts or whatever, AC to DC or AC to AC. You'll always notice on those pieces of equipment 60 hertz, and they're built that way Does a computer have a transformer in it?
Yes.
Yeah, I've got to convert AC to DC. And if it's the incorrect frequency that I put into it in transformation from AC to DC, it's not going to operate correctly. So my entire system is meant to run at 60 hertz.
Professor Shoemaker,
Yes, sir.
you said transformation does not what?
Alter.
Okay.
It does not change the frequency of AC. So if I'm transforming from 7,200 down to 240, I am not changing the frequency of which that is happening. No frequency change happens there. It's coming in at 7,200 volts AC, 60 hertz. And when it's transformed, it's coming out 240 volts at 60 hertz. Any questions on that part?
As well as showing the current flowing, the sine wave also shows how the voltage is varying. Starting at 0 and going through the complete series of changes, through 0 and back to 0 again, we say that a cycle has been completed. The time taken for a cycle is called the period. If in 1 second 4 cycles have been completed, we say the AC has a frequency of 4 cycles per second. In this case, the period, the time taken for 1 cycle, is of course a quarter of a second. And from this we can see a relationship between period and frequency. Period equals 1 over frequency. The 50-cycle AC of the British National Grid has a period.
Okay, so now we're down to 50 cycles per second. And we'll back up on this. The 60 hertz or 60 cycles per second frequency is in the United States. Some other countries use a different frequency. The European nations use a 50 cycles per second. Don't ask me why. Robbie, do you know why? Does anybody know why?
I haven't got a clue.
Do what?
I don't have any idea why.
I don't have any earthly idea either. But if you'll notice, if you've ever been in foreign travel, or if you've gone overseas to the European nations, you always have to have those converters, right?
Yeah.
Yeah. Part of the problem is, 1 is the voltage, and 2 is the 50 cycles per second. You cannot run an American supplied 60 hertz per second. I can't take my computer and plug it directly in a wall over in Europe. I'm going to need something that converts it to be able to work it at 50 cycles per second. So that's the European nations, and I don't know how many others. Why? Again, I don't know.
Period of 1/50th of a second. Incidentally, instead of saying cycles per second, we use the name hertz. In the United States, all electricity is generated at 60 hertz. The AC supply in a ship is usually 60 hertz, 60 cycles per second also.
Oh, question here. What? Does that mean on my battle cruiser that I've got down there, does that mean that thing runs off of batteries? Or does it run off a generator?
Generator.
Right. Why? Can you tell?
Hertz.
Right. It's running a 60 hertz process right here. So I've got generators on board my ship that are producing AC electricity at a frequency of 60 hertz. That's on board a ship. When you see a diesel train that's going down the tracks, is it actually a diesel engine that's making the wheels turn?
No.
Or is that diesel train creating electricity on a generator? Anybody know? Okay. Yeah, a diesel trained engine does not have a direct drive from the diesel engine, when you see the smoke coming out of and the diesel running all the time, to the wheels of the train. That is actually powering a generator, which in turn creates electricity, and electricity drives the train. It's more efficient and controllable.
So diagrams like this are often used to illustrate alternating currents and voltages. And as we heard, this particular one is called a sine wave. The peak value of the current, one way or the other, is called the amplitude of the wave. Sine waves representing AC can differ in amplitude depending on the peak values of the current. And also they can differ in frequency from short peaky waves to broad shallow ones.
Okay, now we're getting the field of more of deeper electronics, and I don't want to take you there. I do want to let you know what we've seen so far is how many times per second in the utility industry we have a sine wave. One sine wave, 60 times per second, okay? How many times does it fall to 0? 3 times per cycle. Hold on one second. Hold on one second. Okay, sorry about that. I had to take care of something right there. All right, so our main process is here, and we're going to dwell a lot on AC electricity. Is you know what a sine wave is, how many times per second a utility industry produces it. We'll get into how it produces it later on in chapters, 60 times per second, and the properties of the sine wave itself. One cycle, 0, 0, 0. It is at 0 3 times per second, and it also peaks at the top and the bottom. This is just direction. This is not a negative and a positive value. It's direction of current flow. Peaking here, but there's voltage present all along the wave until it reaches the middle, where it's at 0. Any questions there so far? Can we unshare that? All right, so back to the book. So they're saying in the book right here, there is a theory called the bump theory, that as far as the movement of electrons, is one electron is bumping the other. So I've got a question for you. What do you think the speed of electricity is? How fast does it flow down a conductor? Any guesses?
Very fast.
Very fast. Okay. I consider my truck at what? Passing Vermelin in his V8. I consider it very fast too. Does anybody have a guess, like the speed of light?
Speed of sound, speed of light.
Speed of light is relatively close to it. Now, there are some factors that are going to go into it. That's how fast, as far as voltage is concerned. How about current flow? We've been talking current flow all morning. Well, guess what? How fast do you think it is? All right, here we go. Share screen. Got you another one here.
Got it.
Electron move down a wire. Which would win in a race, an electron?
Let's go from the beginning.
How fast does an electron move down a wire? Which would win in a race, an electron or snail? Let's answer the second question first. You may be surprised to learn that the snail would win, easily. Let's use this electrical circuit as our racetrack. It has an on-off switch, a battery, and a light. The distance around our racetrack is 22 inches. According to the 1999 World Almanac and Book of Facts, a garden snail can move at a whopping 0.03 miles per hour. That's 0.528 inches per second. We'll call her Joan. The 1998 Guinness Book of World Records says that a garden snail named Archie went a whopping 13 inches in 2 minutes. That's 0.108 inches per second. This is Archie. And here's our electron. We'll talk about how fast it moves later. And they're off. Archie and Joan roar ahead with the Electron. Well, it's moving, but doesn't look like it yet. Joan's in the lead, and Joan zooms ahead with Archie behind, and then the Electron... Well, this will take all day, so let's fast forward it. And the winner is Joan, with Archie well behind, but our Electron has moved a mere 1/10 of an inch. But doesn't electricity move at the speed of light? The speed of light is around 300,000 kilometers per second, or 186,000 miles per second. Actually, in an unshielded copper wire like this one, electricity moves at around 96% the speed of light.
Okay, and I want to explain this a little bit, why he makes this calculation right here. So we're looking at the speed of light moving at 186,000 miles per second. But he's done some computations here, and he only wants to use 96% of that. Do you, in the circuit that he has, battery, light bulb in the process, and a switch right here, why is he using 96%? Why isn't he using the full 100%? Well, for 186,000 miles per second.
Impedance.
Who said that?
Sam.
All right, Sam. Spot on, buddy. All right. There is no perfect conductor. There is no perfect insulator right here. So he's taking into account the copper wire that's going around. He's taking into account also the lamp itself and any kind of impedance that's in the power source itself and the switch. Everything considered here. And he's done some calculations on the conductivity of the wire, copper wire, battery, and the switch and whatnot. And in that computation says, well, I'm not really traveling at 186,000 miles per second as the speed of electricity. I'm going to only take 96% of that. That's why he's making that computation right there.
Light. So 178,560 miles per second. At that speed, ignoring other losses, electricity could circle the globe over 7 times in just 1 second. So electricity moves at close to the speed of light, but the electrons don't, as we saw with our little racetrack. One way to visualize what's going on.
Okay, what's the name of that thing where you take the ball on one end, you let it go, and it hits the other balls, and the other end flies out? Something, Pythagorean something. I'll have to look at it. Yeah, okay. As far as electron and electron movement in a conductor, this, remember, we're still talking theory here, and the theory that I like to consider, as far as the book was concerned. All right, is when one electron moves at one end and starts moving along the conductor, it bumps another electron, and that's the process that's happening right here.
Is to use this row of marbles. When we push on one marble, the effect of that push is passed on from marble to marble, and the result is felt by the wooden tile almost immediately.
So in current flow, an electron is flowed out of the end where the wooden board was, the Scrabble board was, but how much movement was there in the electron? How fast did it move? Relatively slow and short. So that's the bump theory. You're looking at the bump theory in an image right here as far as electron flow.
Immediately. The individual marbles represent individual electrons. They don't move very far along the way. Electricity is represented by the effect on the wooden tile. That effect is passed on almost immediately.
So we talked about, let me go back to that just one moment. Okay. So what do you say the electricity voltage was? Pressure. We talked about that before. He applies pressure to the side. When he applies pressure, what happens to the electrons? They move in a direction, and that is current flow. So I've got pressure, I need to apply pressure, and current is flowing out of the end. It's a good explanation and analogy right there.
The wooden tile, that effect is passed on almost immediately. And to answer our other question, how fast are the electrons moving? The electrons move at a velocity called the drift velocity. Here's one easy formula we can use to find out. Calculating it out, we get 0.0007 meters per second, or 0.0028 inches per second.
You don't need to know all this, I just want to get to the end.
Remember, our slowest snail, Archie, goes 0.108 inches per second, 38 times as fast as the electron. For the electron to go around our 22-inch long track, it would take 7,857 seconds, or around 131 minutes, ignoring the time spent in the battery, switch, and light.
Okay, so if the electron started at the start line right here, it would take 2 hours and 11 minutes for that electron to fully travel the distance back to the battery right here, from here all the way around and back into the battery.
Electricity from a battery is direct current electricity. The electrons go around in one direction. Electricity you get from your wall socket is alternating current electricity. The electrons go one way, stop, go back the other way, stop, and go the other way again. Even here, though, the electrons are moving slow, like we've been talking about, even though the effect, the electricity, moves very fast. So if you're a betting person, bet on the snails to win, not the electrons. Well, thanks for watching.
Okay, any questions on that? Now that you know the difference between DC and AC and the flow of electrons down a circuit, we did bring up one more variable here in our circuit that he had as far as the switch is concerned. And Samuel, what was that?
Impedance.
Impedance, okay. There is impedance in everything that you're going to be seeing out there in the world. It's going to be, there's no perfect conductor out there. So it's going to be impeded somewhat by your entire circuit. Okay, so let's go ahead and stop that share. What time are we holding, V?
10:18.
10:18, Roger. All right, so let's move further on into the book. We've got electron flow. We know the bump theory. All right. I'm going to run up a paint screen right here because you're going to have to define this. And you know, in definitions right here, I'm looking for the facts, man, right? So let me get this rolling. Minimize that. Bam. All right. I'll find my trusty marker right here. So we're going to share a screen. Untitled paint. Share.
Got it.
10:4, thank you. Move that out of the way. All right, so back on page 10, a conductor, for instance, is made of material that contains one or two valence electrons. Conductors are materials that permit electrons to flow through them easily. So if I was to ask you, one, what is a conductor? Get this straight. What would be a good short answer to that?
A device that permits current flow easily.
Well, I would probably say a material rather than a device. There's no mechanism going on here, but that is a very good description. Okay, it's materials where electricity flows easily. Now with this, I'm going to go ahead and say, give me an example of some type of material.
Aluminum.
Yeah, exactly. What kind of conductors are we using on our field? Aluminum. What else?
Copper.
Copper. What else?
Silver.
What was that?
Silver.
Silver. Okay, and we'll stop there. Of the things out there in the world that conduct very easily, aluminum, copper, and silver, in that probably much that order, I think Professor V would agree, are the most used out in the industry. Now, aluminum, probably everything that's going on, and yeah, that's correct, spelled correctly, is probably everything in construction right now. I mean, you're going to find some secondaries that are going to use copper, but as far as your primary conductors are concerned, they're all going to aluminum. One, very cost effective. Two, very good conductor. Okay, and much cheaper than copper. Now, there is still copper out there in the industry now that's been installed, and there's going to be some more installed, but you're not going to use very much of this for primary. Most of your copper installs, because they carry they're better conductor than aluminum, are for secondary conductors that come off of transformers and go into businesses or homes. So not used extensively. And Professor V, jump in on this if you'd like to. We actually went to a good many areas where copper was installed, and it was installed for many years, that we changed it out to aluminum. Was your company doing that?
Yep, still in the process. A lot of copper out there because it's such a good conductor, and then just changing everything out to aluminum because it's so expensive out there to keep that copper on stock.
Right, and you're actually getting money back if you take your copper down and put aluminum up. Two is copper is, wow, it's been around for ever since electricity was invented, probably, and it's getting old and corroded. Okay, silver, I do want to include that. It is the best conductor that we have as far as a metallic material. Now, are my lines made out of silver, my conductors? Any guesses? Do I want to put up a power line that's made of silver that goes for 100 miles?
No.
No.
Oh, no, not cost effective at all. Okay, but all of my switches, like the switches that we have out in the field for the transformers, disconnect switches, transformer switches, they all have a silver plating in their connection points. Okay, and when you have a connection point, you want the least amount of impedance or resistance, and that silver plating on those points where we have switches and making disconnect and reconnect positions or points, we want to have a silver plating on it for the free flow of electricity. Okay, so that's a great definition, and those are three great materials out there in the world that we use for conducting electricity. Okay, I'm moving over to page 15. Materials that are made from atoms that contain 7 or 8 valence electrons are known as insulators. Insulators are materials that resist the flow of electricity. When the valence shell of an atom is full or almost full of electrons, the electrons are tightly held and not easily given up. Okay, so let's talk about it. And you can read it right from the book. What is an insulator?
Isolate two conductive surfaces.
Okay, isolate, watch your word. Am I isolating or insulating?
Isolate two conductive surfaces.
Right.
Electronically isolate.
I'm going to ask this question again. Am I isolating or insulating?
Isolating.
Insulating.
Insulating. What is an insulator?
It's material.
Isolating two conductors.
Who keeps saying isolating?
Sanarella.
Okay.
Is it insulated? The materials used to electric.
Okay. What is an
isolate two conductive surfaces?
Okay, I want you to get away from the word isolating, especially in the industry right here. And we'll talk about that in a moment. All right. All right. What is an insulator? It's a material where electricity flows easily, or what? It's materials that do not permit the flow of electricity easily. Okay. This falls in the same what is a conductor, what is an insulator type property here. Is there a perfect insulator?
No.
No. Okay. There's no perfect insulator. We can add more insulation, but there's no such thing as a perfect insulator. All right. Give me some of the materials that you think are good insulators.
Aluminum.
Aluminum is a great conductor. What insulates?
Wood.
Wood. That's a good one. What else?
Glass.
Glass. Yes, sir.
Rubber.
I could barely hear that one, but I heard something. Rubber, I think it
Rubber.
was.
Yeah.
Rubber is a great one.
Foam.
What?
Foam.
I can't understand that.
Foam. Foam. Like what they spray in your attic.
Foam?
Yeah.
No. Let's stay on the industry. Wood, glass, rubber, porcelain.
Plastic.
Surprisingly, plastic is not a good insulator. Polymer is.
Fiberglass.
Fiberglass, thank you. Okay, those are all good ones that are sticking close to the industry right here. Even though, and I'll bring up a picture here in just a moment, even though these are good insulators, they're not the perfect insulators out there in the world. Now let's talk. You'll have this on video, so be able to see this later. I want to go back on, I think it was, who was saying insulate and isolate?
Sant.
Okay. Let's go file. New. I have a conductor and it's got 7,200 volts on it. And here is my cross arm, my dead end cross arm, and my poles right here. You notice when we've done the dead ends right here, what do we put in this so electricity doesn't flow to the pole? What do we call this part? Insulator or conductor?
Dead end.
Dead end. But is it an insulator?
Yes.
Okay, that's an insulator. All right. I'm going to do the same picture right. Well, let's do a little eraser right here. So that's insulation. If I come in this section of line right here, and I'm just going to do this as a circuitry look. If I come in my line right here and I cut it to where my 7,200 volts can no longer proceed to the dead end, that is isolate. That's isolation. So Sam, does that help explain a little bit more? The difference between insulation and isolation?
Yes.
Okay, good, good. All right, just wanted to get that point, and it's a good thing to bring up because we will have it more into the future right here. Insulate, if this were continuous all the way through. Isolate means I cut the line. There's no more permitted electricity, voltage, or flow being able to go down to the end to the insulator. It's completely isolated from it. All right, what time are we holding, Professor V? 10:30. Good time to take a break. Let's take about 10 here. We'll be back at 10:40. It is 10:40, so we will return here. I've moved up to page 22 in the book. And you'll notice in the center right there is the Coulomb. And that's the first electrical quantity to be discussed is the Coulomb. I'm not going to get into this very much. It's not used in the industry. And the Coulomb does quantify the movement of electrons through a circuit. We really don't need to know that too much as far as the electric utility industry. What we do need to know, and it is a measurement that is used regularly here, is the amp. Okay. The next electrical measurement to be discussed is the amp or ampere. Now it goes through the full description of who discovered it or what it's a measurement of. That's coulombs per second. For our definition, I want you to go over to the next page, page 23, the second sentence down. The ampere is a measurement of the actual amount of electricity that is flowing through a circuit. So it's the flow of electrons that are through a circuit. And if you see my page here, the simple definition, amps equals flow of electricity through a circuit. Okay. Once again, this follows that same electron bump theory, all right, that we discussed about earlier. All right, I'm going to go ahead and discuss here, because we're on the same page. I like to keep these together here. Volts. What is the volts definition? That we learned simply through the water line analogy that we used. What is volts?
Pressure.
Electrical pressure.
Electrical pressure we have on a circuit. I'm not going to include circuit. Electrical pressure. And then what is watts?
Hour.
All right, what is watts definition as far as
Energy.
All right, the flow of electricity and the volts, and I want to get this down straight so you guys have a good working knowledge of how this is. The flow of electricity and electric pressure, that's energy. Watts is measured in power. That's what we use in Ohm's law. But if we had to make it simple, on the conductors that come to my house, I've got electric pressure. And when I turn my light on, remember that part, electricity starts to flow. Power is the light, it's the usage. Output of volts and pressure. Excuse me, volts and amps. Let me erase that right there. And amps. Oh, still erasing. Okay. And I'm going to draw a circuit out here, a real simple circuit for us in just a moment. So those are three good definitions right there as far as the electric utility industry. Amps, flow of electricity through a circuit. The volts is the pressure that I'm applying to it. So let's say 120. Okay. And the usage is the output of the volts and amps. So that's the final product that we're getting here. And it's the use of it. All right. So let's do a circuit here real quickly. Wow. New. Don't say. I'm going to draw myself a little generator here. And out of it comes a wire. Then I'm going to draw my funky light bulb that I'm not good at drawing. And I'm going to have my neutral wire, and that neutral wire is going to be grounded. So let's start with the first one here, volts. And volts explains that I have 120 volts of electrical pressure that's moving, that's pressurized the entire circuit. So there's 120 here, all right? My completed circuit, there's also 120 here until I get to ground. So that's my electrical pressure. I have no switches in here, so this light is burning. The amps is the flow down the circuit through the filament, back out and down and into the ground. And that's my measurement of amps and definition. Okay. The output of the lamp. Now, what does the light give off? It's a light, so it gives off what?
Light.
Light. What else?
Heat.
Heat. Thank you very much. So that is the usage. Volts pressure on the line, amps flow on the line, power light and heat are given off by the lamp. Really easy definition going on there. Let's apply a switch to this. $120-volt generator. Circuit, switch. Light bulb, neutral, ground. All right, and I'll throw this down at the bottom here. Symbology and switches right here, and you'll see this on drawing diagrams. Professor V, correct me if you had something different on your drawing diagrams as far as circuitry was concerned in the utility.
Right.
When you have this symbol, that designates a switch. Now, is that switch open or closed?
Open.
Anybody else?
Isolated.
It's open.
All right, I didn't, isolated was not a option. Is the switch open or closed?
It's open because it's not touching the line.
Okay.
It's open.
Okay, because it's a single line, and what you're looking at is one single line in a circuit diagram out here, it's hard to tell if a switch exists, and this is kind of funky. If I close this switch, my line looks like what?
Straight line.
Yeah, so how do I know a switch is here?
2 lines, I guess.
Okay, we'll bounce back over to this one. This switch here, as far as the line diagram concerned, is actually closed. As soon as I put an O in it, now what is it?
Open.
Now it's open. That O must exist for it to open. Otherwise, if I just drew this straight line right here, and there actually was a switch here, I wouldn't know it because it doesn't show. This thing's going to slam down shut, and I don't even know that it exists. So let's go back. This switch is closed. As soon as I put an O in it, it is open. And that's what you're going to see on your electrical diagrams. Professor V, anything that you've seen differently?
Yeah, the only thing I see different on that, what Duke does, they put a normally closed, normally open on their switches.
Okay, okay. So, and we do that too.
Yeah.
And it just helps you as far as you drive. You're going to be looking at a map, either paper or on a computer.
Right.
And you're going to have this, and it's going to say, is this switch open or closed? I asked that right now.
Closed.
Closed, correct. And it's going to have underneath it NC. Is that correct?
That's correct.
All right. It's going to have NC to let you know that is regular, normal state, day after day after day, that switch is supposed to be normally closed. If you drove up to it and the switch was normally open, you knew something was wrong or something had changed on your system.
Right.
Okay. Then if you had this, you'd have NO. That's the normal operation or the status of that switch in normal day-to-day use. Now, if it was like this, you knew that your electrical circuit had been changed for some reason. We'll get into switching and switching procedures later on. So let's go back to the original. I love this part right here. $120V. Come down here. I'm going to install a switch. Here's my lamp. I'm getting better. Come down here, and I need ground. All right, with my switch normally closed, remember this is a normally closed switch. Do I have 120 volts of voltage pressure completely down this circuit? So is there 120 here? 120 here, 120 here, until it reaches ground?
Yes.
All right, yes, I have 120 volts of pressure on the entire circuit, both into the lamp and out. I'm going to open this switch. Okay. Do I now have 120 volts of pressure here? What do I have beyond?
Nothing.
0 volts. Okay. Samuel, that's isolation. Now you've isolated. Okay. Any questions there? Will my lamp light up?
No.
No. All right. Is there current flow? All right. Do I have amps here?
No.
On this part? No. I don't have any amps along my entire circuit. There's nowhere to flow to. It's like my water line's capped off right here at the open point. So there's no amperage flow in the entire circuit. Last but not least, I'll just go like this in an eraser style. My switch is now closed. I've got 120 volts of pressure along the entire circuit. Are amps flowing along the entire circuit? Yes or no?
Yes.
Yes.
Yes, they are, because I closed the switch. Here's also the big point to remember here as far as safety and which wires you need to cut and isolate. The wire going in from my generator to the lamp, I'll make that a little bit bigger. Professor V, what time is it?
10:53.
Okay. Going into my lamp right here. And the wire that we have coming down here to the ground. All right. This is what they consider out there in the world your hot wire. This is what they consider the neutral. And when I come down, I'm going to a ground rod in the earth. This is ground. Okay, so let's apply a voltage to it. You notice I don't have any switch in it. So on my hot wire, do I have 120 volts? Yes or no?
Yes.
Yes. On my neutral, do I have 120 volts? Trick question. At this moment in time, do I have 120 volts? It's grounded, remember?
Yes.
No, not yet. It's going to earth. Okay. As soon as I open right here and I take ground away, do I have 120 volts here? That's in the first hot wire. Are there 120 volts? I'm not talking amps, I'm talking volts. Pressure here. It's a 120 volt generator. Do I have 120 volts on this line?
Yes.
Yes.
Yeah. Do I also have 120 volts up to the open point?
Yes.
There's your yes. Okay, 120 volts is still applied because I have no ground. Now there's 120 volts on the neutral. I took away the path to ground. Okay. All right, so let me look at the quiz here and we'll go over it 1 second. All right. Sometimes out there in the world, we're going to hook up to an electric motor. So I'm going to apply 120 volts here as my generator. I'm going to come down the line. I'm not good at drawing motors. So here's my motor. Turn the fan. Okay. And I'm going to come over here to ground. All right. Is my motor, when I have this complete circuit here, is my motor my new output? It's not a light bulb anymore. Is it producing something?
Yes.
Yeah, it's turning. So I got 120 volts. Okay, and I'm using amperage. Electricity's got to flow. It is turning, and it is producing a motor, a force, a motor operation, plus it's turning the fan. All right, how do you classify a motor as far as its output? You got your lawnmower. What's it rated in?
Horsepower.
Horsepower, yeah, the engine in your car, horsepower. There's an easy conversion here. All right, an Ohm's law chart. Did you see a horsepower?
No.
No, you didn't see a horsepower. You saw what? Power. Okay, almost there. But motors are rated in horsepower. Here's the simple solution here, and you can look this up on the internet, wherever you want to go. There's a simple conversion going on. Let me get my mouse over here if I can find it. 1 horsepower equals 745.7 watts. That's standard. So I have 745.7 watts of output per horsepower of my motor. So if I have a 25 horsepower motor, how many watts is it using? Nobody's got the calculator out. Let's make this easy. 10 horsepower motor equals what?
Oh, I had it. 18,642.5.
On the 25, correct?
Yeah.
Okay, 18,000 what?
642.5.
Okay, 18,000 watts of usage out of 25. You just took the 25 and you multiplied it by 745.7, correct?
Yes.
Okay. So that's the simple, easy conversion. You're going to get a rating of a product. You look at a light bulb in a house. What's stamped on the top?
The watts.
Watts, right. Okay. You look on a computer back, the nameplate of a computer, and it's actually got wattage. So everything's pretty much rated as far as electronics and things that you consume in your house, your washer, your dryer, your refrigerator, everything on that nameplate of that piece of equipment, its output is in watts. A motor does not do that. A motor is always rated in what?
Horsepower.
Horsepower. But now that we know the solution to that, 1 horsepower equals 745.7 watts, we know the simple conversion right there. Okay. Let me double check these questions right here, and we'll have a, what we got here? 10:59. Man, am I good or what?
You're good.
I'm good. Let me make sure that we've covered everything. Okay. I'm going to unshare here. Okay. And we'll go through the questions for today. Some of these are write-in, and some of these are multiple choice. Some are true, false. Why am I not? There it goes. Stop share. All right, here we go. So, in the electric industry, which type of electricity is used? AC or DC?
AC.
Okay. AC electricity is used in the electric utility industry. All right. AC electricity, is it bidirectional or unidirectional?
Bidirectional.
Bidirectional, travels in both directions. True or false? Insulators enhance the flow of electricity. True or false? Insulators enhance the flow of electricity.
False.
False.
Absolutely correct. Conductors have very low resistance to the flow of electricity. True or false? The conductors have a very low resistance to the flow of electricity.
False.
Very low resistance to the flow of electricity.
True.
Okay. We didn't talk about that. We'll have to do that. Amps current refers to the blank of electricity.
Usage.
Amps. Flow.
Flow.
Volts refers to the blank of electricity.
Pressure.
Pressure. Right. Whoever that person was in the beginning there. Watts refers to the blank of electricity.
Usage.
Usage. All right. How many watts are in 1 horsepower?
745.
745.7.
Excellent. What is the electrical frequency for the United States?
60
hertz.
Hertz.
Hertz. Okay. One more we've got to go over here and we'll have the full thing done. Let me start a share again. Let's see. Paint. Share. All right. One thing to wrap it up here. There was in the book, let me get back to it in the book. Amp. Page 17 in your books, semiconductors. Do I have a share screen going?
Got it.
All right, great. Semiconductors. Semiconductors are materials that are neither good conductors nor good insulators. So they're kind of like middle of the road. Semiconductors are also characterized by the fact that as they are heated, their resistance decreases. So the question itself, and we'll get later on of why we use semiconductors in the electrical industry. But in its normal state, it's kind of middle of the road as far as the material is concerned. All right, it's not a good conductor. It's not a good insulator. So it's in that mid-range right there. But you'll notice in the sentence, semiconductors are also characterized by the fact that as they are heated, when they get hot, their resistance decreases. And that makes them what? A better conductor or insulator. As they are heated, their resistance decreases.
Better conductor.
Better insulator.
Better insulator.
Listen closely. As they are heated, their resistance decreases.
A conductor.
So it turns itself, when it gets hot, it turns itself into a conductor. Okay, so I'll read the question as it would come. True or false? A semiconductor resistance decreases as it is heated. True or false?
True.
There you go. Okay, we'll talk about the usage of semiconductors in the utility industry later on. I just want you to know the properties of it right now. It's neither a good one nor a bad one until it gets hot. Then it turns itself into a conductor. And we'll show you what some of those materials are later on. Okay. Any questions? Wow, that was a lot today.
A lot.
Yep. No questions whatsoever, huh? That must mean I do my job excellently.
I thought so.
Okay. Well, I appreciate your input there, Professor V. Everybody else just seems to think it's Monday and I wish he would go away. All right. I am, just for heads up, I'm still taking, got a couple resumes I'm working on. If you want to submit a resume, please text me and let me know that it's in the ELW mailbox. We'll be looking at those throughout. Is there anybody that spoke with Mark Jones and has not heard back from him?
I haven't.
You have not. Was that Trevon Barber?
No, Reginald.
Reginald? Okay, so he's got, and I'll double check with him. if you could resend me in a text your email address. Okay, and you did order tools from him, correct?
Yes, I was trying to tell him I didn't need the boots. I already had got them.
Well, that's business between you and him. I'll let you handle with him. I just want to make sure he's got your correct email address. So if you could send that to me, then I will send that to him.
Well, he was sending me messages. It's just that I had replied to him about it, and he hasn't responded. 'Cause I think I was one before.
Yeah. My intention there was just to make sure everybody had good communication with him. He'll reply back to you.
Okay.
Okay. Anybody else? Go ahead. All right, Professor V, anything else you'd like to add today?
Field tomorrow morning, 9 a.m.
Okay, that's it. What will be the purpose? What we're going to work on?
We're gonna keep on getting it with the double arm change out, single arm change out, and possibly we have time maybe move into transformer change out.
We'll see on that one. I'd like to get some switch hanging going on. Do a switch. Also, like we said the other day, Professor V are more than willing to climb. I know that some of you are, working with a height situation. We'd be glad to climb with you also. So with that, I think we'll close, unless you've got anything else, Professor V.
No, just to add on what you said about helping climb. I talked to some last week and they were kind of unsure how to maneuver around that guy attachment up on the, on the 40 on the double arm. I get up there with you tomorrow. We'll work it out. Anybody wants to climb with us, we're ready and available.
Okay. Well, if there's no further questions and I think no other input right there, we will be around this afternoon if there anything comes up, and we will see you guys tomorrow morning at 9 o'clock at the field. Looks like the weather's going to be cool, but no rain. Have a good day, gentlemen.